Welcome back to Module 3 of COM 3073. For today's video, I'd like to move on from our discussion of different paradigmatic approaches to communication to talking specifically about the quantitative research methods. By quantitative research methods, I of course mean the systematic approach to collecting, analyzing, and reporting of numerical data. Today, we're going to be covering several key points about quantitative research methods I think you should know before diving into a quantitative study. First, I'm going to talk about the best way that a value-free axiology can be maintained in one's research, that is, through the scientific method. Second, I want you to understand the different components that go into claiming causal relationships. Finally, I'm going to demonstrate how you can construct clear, effective hypotheses or research questions for your study. So let's jump into the content. We're going to begin talking about specifics of quantitative research methods. So this is going to be an introduction to everything you need to know if you want to become a quantitative researcher. From our introductory class, I know some of you might be thinking, look, I'm not going to become a quantitative researcher, and that's perfectly fine. But to that I say, you never know. I've had students in the past who never thought that they would do anything in this field turn out to be things like data analysts and field researchers. The second response I would say is that even if you don't want to become a researcher, at least you can start thinking like a researcher, which will help you in any activity you do, even in, say, fights with your significant others. Although we've introduced the idea of quantitative methods and I said that it deals with numerical analyses, I never provided you with a concrete definition of the term quantitative research. Quantitative research is the systematic study of any phenomenon that's accomplished by gathering observations and turning them into quantities or numbers, then using statistical, mathematical, or computational techniques to locate patterns in these data. So if you're thinking in your head about surveys with scales from 1 through 10, or calculating changes in body weight in an experiment, you're definitely on the right track. Let me give you some examples of possible quantitative research in the communication field. Let's say you as a researcher wanted to answer the question, do speech disfluencies have anything to do with how credible a speaker is perceived? You might randomly split a large group of participants into 3 smaller groups and ask one group to watch a video of a speaker with very few vocal fillers, the next group to watch the same speaker but this time with moderate amounts of vocal fillers, and the last group a video with the same speaker using a lot of vocal fillers. You might then ask the observers to rate the credibility of the speakers on a scale from 1 through 7 on the statement, I thought this speaker was credible, and look to see if there are any statistically significant differences in the scores across the 3 groups. This is a good example of what a quantitative experiment looks like. Next, you as a researcher might be interested in seeing what kinds of things contribute to healthy, satisfying relationships. You might hypothesize that the number of gifts in a relationship is associated with how happy couples report being. So you give out a survey to all kinds of people who are involved in romantic relationships, and you ask them, how many gifts have you received from your partner in the last 3 months? And then you ask, how satisfied are you in your current romantic relationship? You can plot these data and see whether there's a positive or negative association between gift giving and relational satisfaction. This is a good example of a quantitative survey. Finally, you as a researcher who studies developmental changes over the lifespan might ask the question, is there a difference between the frequency in which boys physically aggress versus girls? You and another observer might sit in the back of several elementary, middle, and high school classes and take count of all instances where physical aggression took place. You and the other observer then independently mark whether the aggressor was a male or female, and then after doing some statistical analyses, see if there's a significant difference between the frequency of aggression between genders. This would be a good example of a quantitative coding study. So let's take a step back and recall what you probably learned about in middle school science. The scientific method is a systematic procedure used in empirical research involving prediction making, measurement, observation, and experimentation. After researchers get their data, they also have to analyze the data and draw conclusions about whether their data support or fail to support their initial predictions. You should remember from our discussion on axiology last week that the scientific method is an important set of guidelines to follow so that it allows researchers with a value-free axiological orientation to separate him or herself as much as possible from the research to keep out any biases. So I'll give you an example of how I implement the protocols of the scientific method in my own quantitative studies. We're going to talk about a research project I recently wrapped up addressing the effects of pornography use on its consumers. In the first step, a clever researcher has a question or hunch in mind. In my case, I knew about the great debates on pornography's effects on a wide range of variables including personal body image, sexual aggression, and relational satisfaction. But given the consistent themes in pornography, I was interested in whether there's a relationship between pornography consumption and condom use. So I scoured through our existing knowledge on the two topics and looked through dozens of articles that analyzed major themes in pornography. My search of literally hundreds of different book chapters and articles on the topic led me to the hypothesis that as pornography consumption rises, so does the frequency of sex without the use of condoms. To test my prediction, I sent out a questionnaire to 500 university student volunteers and asked them about their frequency of viewing pornography and their frequency of engaging in condomless sex. After obtaining the data points of 500 or so college students, I analyzed the data using the statistical software package SPSS, but I could have easily done it through Microsoft Excel too. Then I see whether my data support or fail to support my initial hypothesis of a positive relationship between pornography consumption and condomless sex. In this case, I just so happen to be right. So this is the scientific method in a real-world example. Now that we know a little bit more about variables, we're going to move on to talk about the possible relationships between variables. The two relationships we're going to focus on are correlational relationships and causal relationships. The two are similar, but they do carry different assumptions associated with them. For two variables to be correlated, it simply means that as the values of one variable go up, the values of another variable go up or down proportionally. For two variables to be causally related, it means that one variable causes the other, and this type of relationship makes a stronger theoretical claim. You might have heard the phrase, correlation does not imply causation, and that's exactly right. Simply because two things co-occur in patterned ways, it doesn't mean that one causes the other. In fact, John Hume provided us with 4 criteria that must be met for a researcher to claim that two variables are causally related. They are time ordering, covariation, non-spuriousness, and theoretical support. We'll talk about these criteria in further detail in the coming section. But for notation purposes, a single-headed arrow from one variable to another represents a causal relationship, wherein A causes B, whereas a double-headed arrow represents a correlational relationship between variables A and B. Let's take a look at a quick cartoon quote-unquote causal scenario. In the first scene, we see two friends talking about causality, and one man asserts, I don't believe events can be causally related. All we have are correlations, which are by nature subjective. The other friend takes out a gun, the lights go off, and a loud bang is heard. In the following scene, the friend who made the initial assertion about causality appears to have been shot in the shoulder, and the other friend exclaims, "Oh my God, what did the darkness do to your arm?" You can see from this cartoon that the implication was that the friend with the gun asserted that the darkness caused the man's injury, but we know the truth. So let's take a closer look at this causal scenario through the eyes of John Hume. Hume states that for variables to be put in causal sequences, the cause variable must precede the effect variable in time. If, for instance, the man was shot before the lights went out, then we could never claim that the darkness caused the injury because the darkness came after the shot. The second criterion is covariation or correlation. So actually, two variables being correlated is a necessary component for causality. But that makes sense because if two variables are completely unrelated, then there's really no way that one could cause the other. There are two different types of significant correlations of which you should be aware. If you arrange each individual's data point on a graph with one variable representing the horizontal x-axis and the other variable representing the vertical y-axis, and see this pattern of association where the slope goes from the bottom left all the way up to the top right, we call this a positive correlation. If you look carefully at this graph, you can see that as values of one variable increase, the values of the other variable also seem to be increasing for a given data point. So people who score high on one variable are scoring high on another variable. What kind of correlation do you think we call a pattern, whereas the values of one variable decrease, the other variable decreases proportionally? If you said negative relationship, you'd be absolutely wrong. The reason why is that low values on one variable corresponding to low values on another variable is still represented on the same graph. So that would be considered a positive correlation. Now, if I were to say as values of one variable increase and the values of another variable decrease proportionately, that's a negative correlation like we see here. Just as a note of clarity, if the dots are all randomly scattered with no pattern and it looks essentially like the stars in the sky, then there's no correlation between the variables. The third criterion of causality is the element of non-spuriousness. For a relationship to be non-spurious, it means that the association or relationship between two variables is not commonly caused by a third variable. That's at least the dictionary definition, but you may find it a little confusing, so I'll give you a few examples. Here's a hypothetical one. A small rural town in Pennsylvania noticed a troubling trend happening during certain months of the year. They found that as ice cream sales increased, so too did incidences of burglaries in people's homes. At the next council meeting, the council members discussed why this trend, and the only conclusion they reached was that somehow the ice cream consumption was causing people to lose their minds and burglarize people's homes. Obviously, this wasn't the right explanation, but do you know what is? It's likely that the correlation between ice cream sales and burglaries had a common cause that was hiding right under the council members' noses. I'll give you a small, subtle hint. Yes, the sun. Or more concretely, the increasing temperatures during the summer months. During these months, it's likely that the hot weather is causing increased ice cream sales and at the same time forcing people to leave their windows open. When they leave their homes forgetting to shut their windows, their homes get burglarized. This unknown common cause is what led to the spurious relationship between ice cream sales and home invasions. I was reading the Washington Post one day and one of the articles caught my eye. The headline boldly claimed that girls who are overweight are more likely to have acne. I thought to myself, could this possibly be? As I read the article, I noticed the methods they used limited the findings to correlational claims, not causal ones. But the researchers of the study continued to use causal language without making even a good effort in ruling out possible spurious relationships. Can you think of anything that might be a common cause for both the condition of being overweight and having acne? Well, at least two things jumped into my mind. One was the consumption of junk food. Could it be that those who ate larger amounts of junk food were at an increased risk of being overweight and who have skin issues like acne? The only other thought in my mind was simply genes. It could be that being both overweight and proneness to acne are rooted in the same genetic makeup. These were just some thoughts, but if these thoughts remained untested, then we can never claim non-spuriousness of the relationship between overweightness and proneness to acne. Here's an example of some moments in history where we've had remarkable co-occurrences of certain events or attributes, but you can probably tell that one variable did not cause the other. There's a remarkably high correlation between the number of people who drowned by falling into a pool and number of films Nicolas Cage appeared in. You can tell from this graph that there's a high correlation between the per capita cheese consumption and number of people who died by becoming entangled in their sheets. There's also a strong correlation between per capita consumption, this time of mozzarella cheese, and the number of civil engineering doctorates awarded. And there's even a correlation between the number of letters in the winning words of the National Spelling Bee and the number of people killed by venomous spiders. The thing I hope you see from these illustrative graphs is that even though something co-occurs, it doesn't necessarily mean that one thing has any causal relationship with the other. So now that we have the basics of causality, I wanted to key into an important aspect of the scientific method. That is, hypothesizing after we do a thorough search of the entire universe of existing literature on the topic we're addressing. The beginning of all empirical journal articles starts with a general introduction of the topic and a thorough review of literature. At the end of the literature review, several paragraphs are included arguing for a position on the variables of interest. If there's simply not enough information out there to argue for causal or correlational relationships, then you might be better off using a research question. A research question is a non-declarative question asking whether there's a relationship between two or more variables. Examples of research questions include, is there a relationship between news viewing and fear of the world around us? Or, is communication apprehension related to a lack of preparation? On occasions when you can make a cogent argument about the nature of the relationship between variables, then it would be wise to propose a hypothesis. A hypothesis is a declarative statement about the nature of the relationship between two or more variables. There are different types of hypotheses you'll become familiar with through practice. One example of a hypothesis is gender affects self-esteem. This is known as a non-directional hypothesis because you're arguing that there are differences between males and females in their self-esteem, but you're not specifying which gender has higher self-esteem and which has lower. This is also known as a hypothesis of difference because you're comparing groups of people as a variable of gender. If you were looking at variables not capable of being broken down into groups, like minutes spent watching TV, then you would call these hypotheses of association instead. So remember, if you're comparing discrete groups like ethnicities or people of different religious denominations, then that's hypotheses of difference. Anything else is a hypothesis of association. Another example is relational commitment is positively associated with satisfaction. You know this is a hypothesis of association because relational commitment and satisfaction are not inherently grouping variables. It's a directional hypothesis because you're specifying what kind of relationship it is. In this case, it's a positive relationship. When you see the words leads to, results in, or causes, you have what's called a causal hypothesis. To have causal hypotheses implies that you are using methods that allow for causal claims. A key point to keep in mind is that it's only these type of hypotheses and hypotheses of difference where you can determine a cause or independent variable and an effect or dependent variable. The first thing you should know is hypotheses can be directional or non-directional. Non-directional hypotheses make the claim that two or more variables are related in some way, but the nature of the relationship is never specified. It then goes to reason that directional hypotheses specify that direction of the relationship. The words nature of the relationship or direction of relationship might confuse you right now, so let me give you an example. What if I predicted that religiosity affects conscientiousness? Would this be a directional hypothesis or a non-directional hypothesis? Based on my prior definition, it would be considered a non-directional hypothesis because I claim that religiosity and conscientiousness are related, but I don't specify the nature of that relationship. First, what should you look out for when you see a non-directional hypothesis? It often uses words like affects, influences, leads to changes in, or even is associated with, but it never specifies more than or less than something else. But what if I specified that people who identify as religious have higher conscientiousness than those who don't? Then this would be considered a directional hypothesis because you're saying that there's a difference between the groups, meaning religious identity affects conscientiousness, but you're also predicting that one group is more conscientious than another. Hypotheses can be predictions about differences between or among groups or associations between variables. They're essentially the same idea, but it's important to make this clear because it will affect the statistics you run on the back end. Examples again might be helpful in making these definitions clearer. If I hypothesize that depressed individuals have lower relational success than non-depressed individuals, this would be considered a hypothesis of difference because you're comparing differences between two or more groups. Those groups are depressed people and non-depressed people. When you make this versus that type comparisons in a research study where you can put objects or people into groups or categories and compare them on some metric, you're using hypotheses of difference. You could alternatively hypothesize that depression is negatively associated with relational success. The same idea applies, but this time you're not grouping people. Instead, you're acknowledging that there are different shades of depression and relational success from high to low, and so we don't group people into one crude category over another. To identify hypotheses of difference, you often see comparisons of two or more groups, whereas in hypotheses of association, you often see words like associated with or related to. These are telltale signs of an associative hypothesis. The last thing we're going to talk about are hypotheses that propose a causal relationship. In these cases, you'll have an independent variable, which is the variable you think of as the cause, and the dependent variable, which is known as the effect. What if I propose the hypothesis, internet addiction causes occupational or academic problems? Can you identify what the independent variable and the dependent variable are? If you said the independent variable is internet addiction, which is causing the dependent variable occupational or academic problems, you'd be absolutely right. What do we look for in causal hypotheses? You might see the words causes, leads to, or even results in, but most of the time the word cause is used. Now here's a tricky one. If I claim that internet addiction is positively associated with occupation or academic problems, you should automatically think to yourself, there's not enough information to determine the cause or effect. Why? Because remember what I told you about positive or negative associations before. I said that as scores of one variable go up, the values on the other variable will go up or down in patterned ways. The mere existence of correlation says nothing about causation. So if you see any hypotheses of association, you should say that the independent variable and dependent variable cannot be determined. One last thing I wanted to mention was the case of trait or demographic variables in determining cause and effect. What if I gave you the hypothesis that people from Japan self-disclose in lower frequencies than those from the United States? Would you be able to determine the independent variable and the dependent variable? Well, in most cases you might think the hypothesis does not mention cause, results in, or leads to, so my guess would be no. In this case, however, the independent variable and dependent variable can be determined. The independent variable in this case is ethnicity, and the two levels of that variable are Japanese and American, and the dependent variable is frequencies of disclosure. How do we know that? For certain trait variables like sex, ethnicity, height, and culture, they're all considered unchangeable. So in our case, the number of disclosures can't possibly cause one's ethnicity to change. That's pretty much all I have for Module 3. Please review the hypothesis part of this video, as it will undoubtedly help you to complete short assignment number 1. We covered a lot of things today. We discussed the scientific method, Hume's 4 criteria for determining causality, and we addressed different types of hypotheses and research questions and how to distinguish among them. The hypotheses or research questions will often point to or dictate the statistical tests conducted later in your paper, so it's important to be both accurate and precise when crafting them. As always, please let me know if you have any questions about the materials in this video or the class in general. Please don't forget to do the Blackboard quiz associated with this module as well. Have a great rest of your week.